start on time. So it's my pleasure to introduce Dr. Olivier Pinaud, as in Pinaud, which was telling so he's a professor position in Fort Collins and in France. So we have two professor positions. Can go back to France. So it's an interesting topic. I mean, he's a man without a suit who's going to tell us time reversal, so that could be time travel using waves, and we don't have to worry about that. So before we start, I'm going to take a pause and thank Saudi for organizing this colloquium for here. So this is something fantastic. Yep. So we're going to hear this end game result of time reversal for 90 minutes, as opposed to just 1 minute of explanation of time reversal, saying that do the spectrum decomposition on a Mobius strip. All right, go ahead. Take it.
Okay, thank you for the presentation and the invitation. It's my first time here. I'm happy to be driving down. So that's a joint work with Guillaume Ball from the University of Chicago and Matthias Smith in Paris. So that's a work about time reversal and about the control of waves. And it's motivated by some recent experiments, very interesting experiments that were done by Matthias Fink and his collaborators in Paris a few years ago. And so our main motivation here is to analyze these experiments, and we bring new ideas. So there will be 3 parts in my talk. I will start by presenting these experiments. Then I will recall or present the basics of time reversal, which is a field that was developed by Matthias Fink and his collaborators in the 90s. And then I will present our analysis of these great experiments. So let me start. So here's their experiment. So the important piece is a water tank here that sits on top of a shaker. And at some given initial time, they perturb the surface of the water. So that's the perturbation here. And then they look at how surface wave propagates. So that's the picture here. And at some time, so they call that time here TITM, they shake the water tank. And they do it in very fast way and very strong. Okay, so these are the perturbations here. This is the acceleration. And you see you have the spike and it's very short. And then so that they have a camera and they look at what is happening at the surface. So we should have a video of this. So that's from their paper. Okay, so that's you're seeing the top of the water tank, perturbation, the wave propagates. Okay. Then they shake the tank, and you see a backpropagating wave that refocuses exactly at the emission point. Okay, so I have another one that's maybe even more interesting. So they're in Paris, so they have the Eiffel Tower. They perturb the surface. Then at a given time, they shake the tank. And somehow, miraculously, they reform the Eiffel Tower exactly at the initial time, if you look at it at the right time. Okay, so our main motivation here was to understand how this was happening and quantitatively understand the properties of the refocusing wave. And so we need to model this. And so what happens is that by shaking the tank, you're changing the constitutive parameters of the equation modeling the propagation. So supposedly these are shallow water or surface wave equations. And by shaking the tank, you change the velocity of the wave, you change the gravity. And this equation explicitly depends on gravity. So by changing the gravity, you change the coefficients in the equation. Okay? And by doing so, you create a backpropagating wave. Okay? Now we see that this works because the tank moves very quickly and with high intensity. And so we want to understand why this is happening and how can we quantify the refocusing of the wave and what are the different parameters that parameterize the quality of refocusing. So if you have any questions, just stop me.
So you just change gravity for a little time?
Right, very short
And
time.
gravity goes back to what it was?
Yes, we shake it very quickly. So before going there, I want to present the main ideas behind time reversal. So that's a concept that was introduced by Matthias Fink in the 90s. So many people have studied that phenomenon. So I'm citing here just mathematicians, but I guess there are at least the same number of people in physics and humanities. Okay. And so the main original idea was to exploit the fact that you take the wave equation, okay, simple wave equation, and you change the sign of time, you're not changing the equation. It's invariant by changing the sign of the equation. And so this idea was exploited in the following way. So there's a three-step procedure. Okay, so you emit some signal. Say time equals 0. Then you let the signal propagate over the time t. So you go from 0 to t. So that's forward propagation. So see the surface wave, the spherical wave propagating in the picture. Then at a given time, you reverse the signal. So that's something that's not trivial at all because you have to measure the wave field. So here you have several possibilities. Either you measure the wave field over a volumic domain if you're in 3D. So you need to know the wave field everywhere in the domain, which is not easy to do. And in practice, that's not what people are doing. In practice, they measure the domain over a surface, but for all times. Okay, so you need some 3D information. You take, whether you take 3 spatial dimensions or 2 spatial dimensions plus time, you're fine. It's equivalent. And so, at that time, capital T, you measure the wave field. So for the wave equation, you need to know u and its time derivative. Reversing the signal means keeping u fixed, the sign is u fixed, and changing the sign of the time derivative. Okay, so it's equivalent to changing the velocity. And then you let the signal back propagate for the same amount of time, and you get something that I call u star. And so, depending on how much of the field is measured, so if you measure the entire field, the u star will be exactly the same as the initial condition. Or if the medium of propagation is very heterogeneous, in the sense that there's a lot of scattering in the medium, in that case you don't need to measure the entire signal. If you measure just a small fraction of it, you have as much information as if you were recording everything, and the u star that you get will still be close to the initial condition. Okay, so this idea of time reversal is a real success story. Matthias Fink started a few companies, three or four, I think, with applications in telecommunications, medicine, non-specific testing. And I think these companies now employ like 100 people. So these ideas were very successful.
In heterogeneous media, or this one is homogeneous media?
I'll show you both.
Okay.
Yeah. So in that media, it's homogeneous.
Okay, right.
But you measure everything because you're well, we'll get there.
Okay.
So I want to show you movies of like classical time reversal. So this is an initial condition. Okay. I'm going to let it propagate. I'm going to record the entire field over the whole domain. I'm going to change the sign of the velocity, the time derivative, and I'm going to let it back propagate. Okay, so the wave propagates, reversal, and what you obtain up to numerator errors is exactly the initial condition. Okay.
when you back propagate it, it's already numerically or
Yeah, everything is numerics. Yeah.
the back and forth?
Right, right. Okay. So here I have that rate resolution. My Gaussian is exactly the same as before, up to numerical errors, because I have measured the entire wave field. Okay. So let's see what happens when okay, I am just measuring the wave field and returning it on a small fraction of the domain. Okay, so same as before. Propagation. I'm going to just measure something here. Boom. So just a portion of the wave is back propagating, and you see, of course, you've lost a lot in resolution. It's classical diffraction here because you've not measured the entire wave. And since you make measurements in that direction, you have a pretty decent resolution in the transverse direction here, but here you have essentially no data, and so the resolution is bad. So now, similar experiment, okay, where the wave propagates in a highly heterogeneous medium. So I model that heterogeneous medium by random media. So, okay, I've generated media with Fourier series, and so the wave will propagate. I'm going to make measurements over a small domain around the initial support of the wave field, and I'm going to return just that small fraction, not the entire wave field. Okay, so wave propagates. You see the interactions here with the random medium. Oh, I'm reversing just a small part. Oh, and then this is what I get. Okay, so here you have, it's not perfect, again, there are numerical errors, and it depends on the interactions between the wave and the random media, but you get essentially the same resolution as so you get the same initial condition, the same shape of the initial condition here. Okay. And so that's because of an interaction between the wave and the random medium. So there's some mixing. That means that you don't need to make measurements over the entire domain. By making measurements over a small domain, you have almost as much information as you have when you make measurements everywhere. That's because of the mixing. Okay. So that's an important idea in time reversal. The more heterogeneous the medium, the better the time reversal will be. Okay, so okay. So now let me move on to the original experiment in the light of what we've seen before. So we'll start by modeling the experiment by time-dependent media. So the coefficients depend on time, because when you shake the water tank, you're changing the coefficients with respect to time. So we analyze the refocusing wave when the background is homogeneous, no random media. And in the second step, we'll see what happens when the medium is random. And we hope to observe the same super resolution as we had for classical time reversal. And if I have the time, I'll say something about the constant particle case, which is interesting.
So what's the boundary condition here?
In the simulations, I put directly boundary conditions. So
Homogeneous.
yeah, I stopped the simulation before. I could have added PMLs. I didn't want to. Okay, so we will model the wave propagation by the simplest possible system here, so the acoustic system. So that's reasonable approximation for weak perturbations. So the appropriate equations are shallow water equations. If you linearize them, okay, you will get the acoustic system here. So what are my unknowns? So rho is the density of the fluid. Okay, so it's a function of time. V is the velocity, P the pressure, and kappa the compressibility. So we're solving these equations over a given domain. And so, since in the experiments, the shaping is done in a very quick way. We need to model these coefficients by singular functions. And they will be singular in time. Okay? So ideally, we will take just delta functions. So you have a background and you perturb that density or that compressibility by a delta function. And so, first we need to make sure that the equation makes sense. And for this, we will need at least one of P or V, the velocity, to be continuous in time. Okay? And so we see here if it's possible to have one of these two coefficients, or possibly these two coefficients be the delta measure, and one of the V or the P to be continuous in time. So, okay, so let's try the simplest thing that comes to mind. So I keep the compressibility constant in that equation. Does not depend on time. Smooth kappa, and then I perturb the density by a delta function at time t to model the shaking of the tank. So, okay, do this equation make sense? So here you see I have the delta function in time. I'm multiplying the delta function by some function. That only makes sense if the function is continuous. So I want the dv dt to be continuous. Is it possible for that system of equation? So if I have a delta here, that means that the p is a delta. Here I'm differentiating the delta, and I have v. It's not looking great. So if I perturb the density in this way, there's no way I can give a meaning to this expression.
Aren't you making trouble for yourself by insisting on using delta functions?
Right, but that's the... Of course you can realize that, but the true model behind it is the delta function. You have a spike. So I can put epsilons, that's what I do at some point. Put epsilons to regularize this, but the true model describing physics here is going to have a delta function.
There's no such thing as delta function.
No, but that's what I'm saying. You can regularize it, but at the first order, the leading order will be described as a delta function. It's just that I'm not putting the delta function in the right place. Here. So now, and it turns out that's what happens in the experiment. Of course, the delta function is at the right place in the experiment. So, okay. Now, let's imagine we perturb the inverse of the density. So, the equations are usually written in this way. That's why you want to perturb the rho first. But nothing prevents us from multiplying by rho minus 1. Let's see what will happen. Okay. And then we decide to perturb rho minus 1. So we put the delta here now. And that makes a big difference. Because here, to make sense of that equation here, we need P to be continuous. And let's see if this is compatible with this equation here. So if I have a delta, I'm integrating so delta to get V, so we'll get discontinuous function. Fine. And here to get P, I'm integrating my discontinuous function. And therefore I will get a continuous function. So P will be continuous here. And that means everything makes sense because I'm multiplying the delta by a continuous function. Okay? And so interestingly enough, that's exactly what you find in the experiment. If you look at the linearized shallow water equations, the gravity term is right here, not there. And so when you perturb the gravity term by a delta function, by a spike, you're exactly in that setting. Okay?
You're doing a weak sense, right? This one. I mean, when you do the hand waving, without hand waving.
Right, right. Here, I even don't care about the gradient of P in space. Space does not matter. Here, I just want to see if in time I have sufficient regularity to make sense of these equations. But whether you write the weak form, of course you have to write the weak form.
This has to be, I mean, this makes sense only in the weak form, makes sense.
Right.
Otherwise it doesn't.
Right, right. But even in the weak sense, if you don't have a continuous function there, it's never going to make sense.
Yeah.
So once you make sense of that term, then you choose whatever formulation you want. Okay? So, okay, at least we have this settled. And, well, we can ask, okay, what if we perturb also the compressibility? Why not? And then everything breaks down. Because if you have a delta function on that side, well, the p will be a discontinuous function. It doesn't work. So that does not mean you don't have solutions. That means that you don't have continuous solutions. You can construct discontinuous solutions, but in that setting, we will see that you will not have time reversal. In order to have time reversal, you need one function to be continuous. Otherwise, you don't have reversal. Okay. So here the summary is that we need at least one of the coefficients to be smooth. So let's choose kappa, for instance, and we need to perturb the inverse of the density. Okay. So now let's rewrite everything in a more convenient form. So instead of taking delta functions and regularizing them, okay, I'm approximating my delta function here by some function beta tau. So tau would be the time width of the regularization. Key is a characteristic function of the domain where we perturb the coefficient. So in the experiments, these were the entire domain. The entire tank was shaken. Now I can look at what is happening when I'm just perturbing the system in a small domain. Okay, so the interest in doing that is to look at the random case and to observe super resolution. See that later. So that's my perturbation. And then for the mathematical analysis, I'm rewriting the acoustic system as the first order hyperbolic equations, very classical in the field. So A is just a diagonal matrix, we can forget about it. The dg's here are just some constant matrix as well. And so this is the unperturbed part. Classical wave equation here. U is the wave field. So the first three components are given by the velocity. Velocity that is here. And the other component is the pressure. And so I'm putting then the perturbation on the right-hand side. Even though I do not know the right-hand side. So it looks like a source term in the PDE, but I don't know it. The source term is proportional to the gradient of P here and the perturbation, and I don't know P because it's a solution to the equation. Okay. Now I do that because you see that's the proper way to understand how that back-propagating wave is generated by the perturbation. Okay? So, okay. And so once you're there, then the main idea is to write properly the wave field. And so we have the decomposition that is completely artificial at that point. You can write any solution to the wave equation in that form. So we have capital U, which is the unperturbed solution. So there's no V. That's the solution of that equation, and V is 0. For some appropriate initial condition. UR is a reverse wave, so it doesn't mean anything at that point, but we assume. UF is a forward wave. And R here is a reminder. And as I said, this is completely artificial in the sense that the reminder could totally absorb all these terms if it's not small. And in general, it's not small. Okay? That's why this is artificial. But we'll see that in the context of the experiment, that particular reminder is small. If the tau is small, so tau is the extent of the perturbation, the time extent of the perturbation. So if the perturbation is very quick, okay, then the tau is small, and then we will see that the reminder here is small. That means you can forget about it, and that your wave field is described by the unperturbed solution, a reversed wave that we will characterize, and then a forward wave. So this time, reversal property in the experiment holds because of this R is small. And so, since this is the main player here, I will explain how we get that expression. So, for this, I will introduce the Green's function of the unperturbed equation here. Okay. I think everybody's familiar with Green's functions. Okay. So this is just a notation. something simpler. And so I want to give you an idea of how we get this, and we need the form of the reminder. So I'm just using the AML formula here. Initial condition, so Green's functions apply to the initial condition, and then Green's function applied to the source term. And so then there's a very simple trick, and everything comes from that trick. So here's the source that I don't know. Part of the solution, the source. Since I don't know it, well, I'm just going to replace it by the equivalent source for the unperturbed equation. Okay, so in the perturbed case, my source is gradient of little p, which I don't know. I'm replacing little p by capital P, which is the solution to the unperturbed system. So by doing so, of course, I make some error. R, and so R is simply the Green's function applied to the difference in the source term. Okay? So let's forget about the remainder for a minute. Let's call that term B here. And here in the source term, we can use the PDE to rewrite the gradient of P in terms of the time derivative of the unperturbed velocity. Look.
Can you remind me what the unperturbed problem was?
So the unperturbed problem is the system here with V equals 0. Okay. You don't perturb the background. Okay. Okay. So I can use the PDE. I'm replacing gradient of P by this TV. Forget about the and so then the B that we have here is independent of the perturbed solution. Just a reminder depends on the perturbed solution. Okay. So now let's analyze the B here. Okay. And so you see here we have dTV. That looks a lot like the time derivative of the full wave field if we add the time derivative of the threshold here. And so, okay, let's add it and let's subtract it. Okay, very simple trick. 1/2 of V, I'm adding dTV, and I'm subtracting it. So that piece is the time derivative of the unperturbed wave field. And what is that piece here? Well, if you introduce that matrix gamma, which is usually called the time reversal matrix, so that's the matrix that changes the sign of the velocity, sign of the V, with keeping the sign of P. If you introduce that matrix, you can rewrite the second term here as gamma multiplied by the time derivative of the unperturbed field. And so at the end of the day, in the term B that was here, you can replace the S0 by the sum of these two quantities. And there's one wave, so one term that we'll call UR, the reversed wave because of the time reversal matrix here. And one that we'll call UF because it will be a forward propagating wave. And so something that's important here is that this is not the wave field that appears in the equations, but the time derivative of the wave field. Okay, so then the next question is, when is the remainder small? So, again, let's just have some hand-waving arguments. Okay, so the error term here is the difference between the perturbed and the unperturbed sources, multiplied by the perturbation here. Okay, so that's why we had this. Gradient of P, gradient of capital P minus gradient of small p. And here, this is the approximation of the delta. So let's just suppose we have a delta here. And we want to show that this is small. So why is that? Well, so I'm looking at that term at the time of the perturbation. And I'm formally introducing T minus, which is the time right before the perturbation kicks in. Okay? And I'm subtracting the gradient of little p, and I have to add it. Now, right before the perturbation, Well, the perturbed field is the unperturbed wave field, 0 here. And then if I suppose that I have some continuity in P, which is something we tried to get from the beginning by putting the delta function at the right place, if this is continuous, forget about the gradient, this is exactly 0. Okay. And so we can formalize this. This is actually true. We get some estimates on the P, and we have the right amount of regularity. We even have that dt P is not. Okay. So this argument here can be justified. Maybe I'm going to skip this. So we can do the same kind of tricks in the case where we replace the delta function by an approximation. And in that case, we get an error estimate like this one here for the remainder, and the error is proportional to the size of the perturbation in turn. Okay, so if you have a large perturbation, well, the remainder would not be small. Okay, so that's what I was saying in the beginning. This is completely artificial. The decomposition there is completely artificial at that stage because we have not precised the size of tau. Okay, so in general case, there's no reverse wave. Okay, so now that we know that the remainder is small, if the perturbation is small enough, let's look at the structure of the reverse wave, the Eiffel Tower that was backpropagating. So what does it look like? So remember, we have that term, the Green's function applied to the time derivative of the initial field. And so if you suppose that the perturbation occurs over the entire domain, remember V is that function here, and the P represents the domain, spatial domain of the perturbation, so suppose it's everywhere, then what you get, if you look at that term at the proper time, which is 2t, propagate over times t, then you backpropagate t, then what you find is a weighted average of the time derivative of the initial field. Okay? And the weight is given by the shape of the perturbation. And so if it's a delta, you get exactly the time derivative of the wave field. So what's backpropagating, so it's hard to see on the experiments, but what is backpropagating is the time derivative of the field, not the field itself. And so that comes out from the equations. And if you look at the forward wave, after the time of the perturbation, what is propagating forward is the time derivative of u. So by that trick of adding and subtracting terms in the wave field, you're creating a backpropagating wave here, proportional to dtu, and forward propagating one proportional to the okay. And so you can rewrite things in a different way. So here you have the linear combination, okay? You can write everything in terms of a kernel applied to the initial condition, so the physio is by the initial condition. And you can look at the resolution associated with that kernel and see what influences it. So in some simple situations, we'll give you the details. The kernel, so that expression here can be written as a convolution. And so the refocused signal, so if you look at just at the pressure component, is the convolution of some kernel and the initial condition here, and the kernel is simply the Fourier transform of the perturbation function here. So what matters here is the argument, and you see that you have tau multiplied by the Fourier variable. That means that if the largest wave number you have in your initial condition is smaller, well, if the tau here is smaller than the largest wave number in the initial condition, then this is almost a constant. Yeah. And if the Fourier transform of f is almost a constant, then it's almost a delta in Fourier space, and when you convolve with the delta, you get almost the original function. So the condition for having good resolution here is that the tau must be much smaller than the spatial variations of the initial condition. And so that's why they have a very short peak. So the initial condition is the Eiffel Tower, which is a singular object if you model that as a function. Okay? And so to correctly generate backpropagating wave, you need a very fast perturbation because the initial condition here has fast variations. And so morally, that operation here is a low-pass filter. Okay. The high frequencies will not be time reversed well, but the low frequencies compared to down here will be. Okay. So this is just what I expect. You get a delta when tau is very small. Okay, so let me show you some simulations. So that's my initial condition. Okay. And so here the most singular perturbation you can do numerically is a time perturbation over the time grid. So call it h. Time step size, I put a delta, something very large over one time step, and then I keep it. Okay, so that's my perturbation. So here's what you find here is actually what has been focused for perturbation of duration h. So it's the most perfect. And then, so if you increase the width of the perturbation, as we just saw, you lose resolution. So that's what you find here. So here you have 5h, 7h, and then here 30. So it gets blurrier and blurrier. And it's simply because you are time reversing wave at different times, not at the same time essentially, and so there are destructive interferences, and you don't get the same resolution. Okay? And so here's something that's actually interesting. Well, what if we perturb several times? And so what happens? So the wave propagates, shake the tank once. What happens is that you create a backpropagating wave proportional to dTu, but then you have two forward propagating waves. You have the unperturbed one, u, and then dTu. And then at time 2t, you shake the tank again. And so by shaking the tank, you will time reverse u plus dTu. But by time reversing that, you will create a backpropagating wave that will be proportional to dTu plus second derivative of u. Okay? And so then if you use the fact that we model, so if we accept the fact that modeling the surface wave by a wave equation is correct, then the second derivative of p will be the Laplacian of the initial condition. And so if you shake the tank twice, okay, and you look at the time 2t, what's coming back, that's the Laplacian of the initial condition. So you can compute Laplacians with a water tank. You can make measurements. Okay? And so of course you can repeat this as much as you want. So essentially shaking the tank acts as a differentiation. So in time or in space you can exchange with the modeling equation. Okay? Okay, so now I'm interested in comparing with classical time reversal, where we perturb the coefficients only over a small domain. So remember the simulations, the classical simulation for the time reversal, when we measure the entire signal, we get the initial condition perfectly. And when we make measurements of a small domain, we lose resolution and we do not get the initial condition as well. So here that's done. So I've perturbed the coefficients on these two disks here, so small disk, and here a larger disk. Okay? And this is what I get. Okay? So for the small disk, it's hard to tell anything. There's no smiley. So again, we have a decent resolution in the transverse direction because that's where we make the measurements. So this is just a fraction of the simulation domain, but these are the real distances here. And so I have some information in that direction. So I have good resolution in the propagating direction, but the traceless one doesn't work. And over the large disk, it's a little better. It's still not great. So then the natural question is what happens if the wave propagates in a heterogeneous medium? And see whether we observe super resolution as in classical phenomena. So the idea is to put a random medium here, perturb the coefficient only on this small disk, and see what are the results. So maybe one is not that. So we want to do some analysis as well and characterize the form of the refocused wave. And so we need to model for this the random medium. Because it, again, the factor that brings super resolution is the mixing between the wave and the medium. So we need to have some idea about how the wave and the medium interact. And so to do that, so we need to introduce some scales. So here my small scale, epsilon, will be the typical size, spatial size of the initial condition divided by the overall size of the domain. So here I'm going to make some high frequency assumptions. So epsilon is small. This is my initial condition that I suppose is centered around some point x naught and with a spatial extent epsilon. So everything is really scaled properly. Okay. And so then we need to model the medium. So this is my background. The unperturbed medium, so there's no time dependent perturbations here. And so I have some average here. And then I have some random perturbations of the average. Okay. Same for the compressibility. And what matters here are how fast are the random oscillations and what are their strengths. Okay. So there are a few interesting models that you find in the literatures. They're pretty classical. So one is when the fluctuations of the random medium are much slower than the wavelength, for instance. Okay, so in that case, geometrical optics is a good approximate model. So essentially, you can model the propagation by particles propagating in a random potential. So, and then you suppose that the amplitude of the fluctuation is sufficiently small. There's another regime that is interesting. That's when the wavelength and the correlation length are comparable. By doing so, you maximize the interaction between the wave and the underlying medium. There's another regime that's not interesting. That's where the wavelength is much larger than the fluctuations in the medium, because in that case there's little mixing. You can accurately describe the propagation by propagation in effective medium, and in that case there's no mixing, and so the result will be just the same as if we were in a homogeneous medium. So we can do the whole analysis. I'm going to skip the math here. So the idea is the same. But at the end of the day, we have the convolution between some filter and the initial condition, and we can completely characterize the filter. And it turns out that when the waves propagate in the random media, the filter becomes more localized in the real space than if it were propagating in homogeneous medium. And so I've considered like two random media. One that corresponds to the geometrical optic regime. This one here. No, so that's the other one. Okay. So that's this one. So we have fluctuations at the slower scale than this one. This one is almost white noise. So oscillations of the medium are very fast, and here they're slower. And so here are the results that we have. So in the top row, we have what I call the smooth random medium. Sorry, this one. And the bottom row is the rough one, white noise, of course, here. The left column is the small disk, and the right column is the large disk. So clearly the best result is here. The larger that is, the better. Of course, the more information you have, the better. And also, the rougher the fluctuations, the better. And that's because here you see my initial condition is a singular function. And so we want this to interact well with the medium. And this will interact very well with the medium like that because the fluctuation is very fast. While here you see the interaction is not strong. There's still some interaction, but it's not strong. And so you see how you can see the smile here, but not as well as here. So you have noise in the background, of course, which is not measuring the entire signal. That's why the mess at where you make the measurements. Okay? But still, you observe very good resolution here, even though we measured just a fraction of the signal. So we have essentially the same effect as in classical measurements. So like from a practical viewpoint, that could be interesting because you may not have to perturb the entire domain, just perturb one fraction of the domain. Okay. And if the medium is sufficiently heterogeneous, then you have good resolution. And something I forgot to say that's very interesting is that here there's no measurement. Okay, for classical time reversal, you have to measure the wave field. It's not completely trivial, right? So that's the way they do it. Usually it's transducers that can act as sources and as receptors. And so you measure the signal, and then you have to re-inject it in the domain. Okay, so from an experimental viewpoint, it's very hard to do. So of course they know how to do it very well. But this is not completely trivial. Here there's nothing you can do. You just shake the tank and you generate that back propagating wave. So from an experimental viewpoint, this is interesting. This is much simpler than the usual time reversal. So I guess I have 3 more minutes, right? 50?
5 more minutes.
5 more minutes, okay. So this is the point spread function. So I start with very localized Gaussian, and I see what I observe. So again, I have something very sharp here, and it gets worse and worse, depending on the medium or on the size of the disk. Okay, so this is my last slide before the conclusion. So there's an interesting case here corresponding to the constant impedance. So the impedance is a physical quantity that helps describing how waves are scattered when going from one medium with a set of parameters to a medium with a different set of parameters. So typically, if the impedance is constant, then in amplitude there's no reflection, it's just transmission. And so how can we look at that case here? So I'm just rewriting the original equation in the following form. So the A0 models the unperturbed propagation, and the A1 corresponds to the perturbation, and the perturbation appears only on the diagonal. So I have a diagonal matrix here multiplied by the unperturbed system. And so what is the definition of the impedance? The impedance is the ratio of the density and the compressibility. So suppose it's constant in time. So I design some experiment where I can do whatever I want to the density and the compressibility, but keeping this constant. And so if this is constant, that means that I can factor out the 1 plus, say, 0 here. Okay? I will have to divide here, but assuming that the impedance is constant, I get a constant number. Constant in time is this. Something constant. Okay? And so if I look at the equation here, that just becomes the equation here. Unperturbed solution multiplied by this, that depends on time. If you solve this, okay, so this is a hyperbolic system, so the eigenvalues will be purely imaginary. Okay, and then that means that the U will just see a phase shift. So you can have as nasty as you want perturbation. The only effect on the wave will be a phase shift. So it will be a discontinuous function. Right? Before the perturbation, nothing. Right after, when you pick up the phase. And so in that case, there will not be any time reversal because the function U will not be continuous. So the continuity was a criterion for having time reversal. So that's a nice example, because I guess you can put just any perturbation here as bad as you want, then the wave will not see it, just the phase shift. Okay. So let me conclude. So a time reversed wave can be generated without any measurements, simply by changing the medium for propagation. To observe a good resolution, the perturbation has to be sufficiently fast, and how fast depends on the frequency content of the initial condition. From a mathematical viewpoint, we need to pay attention to where we put the delta function, so the equation makes sense. Then to observe time reversal, we need some regularity in time, so that the error term is small. Multiple perturbations act as a differentiation. Okay, we can compute any power of the Laplacian at that point in time. And so, well, this is just the beginning. We'd like to have a more complete theory. Here the estimates I show you would come in the whole space when coefficients were constant in space, so we can use Fourier transform and I think it's fine. We'll be interested to generalize that to non-spatial constant coefficient. I don't think it's that trivial, because you really have to do a fine analysis of what is happening because of these delta functions. And maybe a more interesting question is the control theory. Well, so far we've generated a backpropagating wave. Well, can we do something else? Can we tailor the shape of the perturbation to get different types of waves? But so this we don't know. Other questions is well, what happens for electromagnetics? It's a little more complicated in electromagnetics because then you have tensors, permittivity, permeability of tensors. What if you perturb just one coefficient in the tensor? I don't know how you do that experimentally, yeah? But why not? So elasticity as well. So we'll see, to be continued. Okay. Thank you for your attention.